Okay, so last class we stopped at the Cauchy's equation, and just to recap, this is the form of the equation, and what we saw the limitations of this equation toward being unsolvable to get to any sort of solution is primarily because of the number of unknowns and the number of equations available. So just to put this into perspective, in the Cartesian coordinates, the Cauchy's equation has the parameters density rho, u, v, w, which are the three velocity components, and then you have the stress tensors, sigma, in the 6 components of the stress tensors in the x, y, and z coordinates, right? So So these are the 6 components. So total there are 6 plus 3 plus the density term. So 10 unknowns. And how many equations do we have? We have 4 equations, which are 3 equations from Cauchy and 1 continuity differential equation. That's the mass. So there are 6 more equations needed. 6 more equations needed, which, if in order to make the Cauchy's equation solvable, and these 6 more equations, what we call it as the constitute equations. So the challenge which has been posed in the late 1800s has been, how do we actually go about figuring these 6 more equations and pretty much come up with a way to attack this problem in fluid mechanics. So it took a mathematician and an engineer. This is what we call this a Navier Stokes, this pair, to sort of come up with the solutions, and this particular segment of the chapter is all going to be about that. So Navier Stokes could be also called as the modified Cauchy's equation, and essentially it is a momentum balance equation. Okay, and as I said, why Navier Stokes equation came into place is because of these limitations of the Cauchy's equation, and it is a step-by-step process, and we will go through the different steps as was done to actually come up with the analytical expression of the equation. Okay, but one of the things to note here is that for the scope of this class, this equation will only apply to Newtonian incompressible fluids. Okay. All right. So what is the first step? In the Cauchy's equation, the big elephant which was which was not addressed was the stress tensor. So one of the things what we do is we separate the stress tensor into pressure stresses plus viscous stresses. And you probably already know from chapter 6 that when we do force balance, we have the pressure force acting as well as the shear or the force which acts in response to the friction between the fluid and the walls of the tube. So what we do here is that we separate these forces stresses out, the shear stress, the pressure stress and the viscous stress, and we get the sigma ij tensor into this particular form, minus p 0 0, essentially a very nice. You can apply matrices for tensors, that's one of the beauties of it, plus the different matrix elements of the so this is the viscous stress tensors. Okay, so some of the properties of these different tensors is that the pressure tensor, as you have seen in previous classes, acts only in normal direction, exists for fluids at both rest or in motion, and for incompressible fluid, P is also equal to the mechanical pressure. For the viscous stresses tensors, these only come into play when the fluids are in motion. Okay, now you might be wondering, wait a sec, we probably have opened up a can of worms here. It was much more simplified with just a sigma ij stress tensor. Now you have the pressure tensor as well as the viscous stress tensors added on. So we have way more unknowns, plus we don't know P either. Okay, but what do we certainly know? That is something. But how can we, why have we done this? Because we know the relationship between stress tensors, or in particular stress, which is a function of viscosity and velocity. Of course, the exact function depends on the type of fluid. Okay, so just to recap, what do we know? Recall from chapter 4, we have this shear stress graph as a function of strain rate, which is Eij, and the relationship between shear stress and the shear strain rate is 2 mu Eij, where Eij is a strain rate tensor. And for more details, see chapter 4. Okay, so we use this relationship to further simplify the shear stress tensor in the previous step, and further we also consider incompressibility and isothermal conditions to this particular problem. Why we use isothermal? Because temperature is another parameter. If we use isothermality, if we apply this assumption, we avoid energy balances, which is a big convenience at this particular stage when we are trying to shrink our number of parameters. Right? So these are constant. Plus you have, because of incompressibility, you have also these particular things constant. Okay, so let's move on to the next step. So we rewrite the stress tensor now in terms of the relationship what we derived. So essentially we have replaced the xx, xy, xz components using different relationship between viscosity and shear stress. Okay, so your sigma ij, now the shear stress tensor, becomes the pressure tensor plus the tau ij. Okay, now for cylindrical coordinates, please check out the equations 9.63 in your text. Although this is, I will probably not be asking any questions in your exams on the cylindrical coordinates, but if those of you are interested, you can check it out. Now when you simplify the complete equation, what you find here is that the sigma ij, the stress tensor, is equal to the pressure plus the viscous stress tensor as expressed in terms of change of velocity, or the function of velocity and viscosity. Okay, so that is pretty much what we said, that we are making tau as a function of velocity and viscosity. That is our objective. We have been successful in achieving this. Okay, next step is we substitute the common expression what we now have for sigma ij for common fluids into the Cauchy's equation. And what do we get? So this is so sigma ij equal to p plus tau ij, and the expression what we get, this is just in the u, in the x component we are plugging in, but also note that whatever answer we get will also we will also have separate equations for y and z components, but that will be of the similar form. Okay, rho gx plus where you have pretty much this particular expression this is equal to this, then you have this expression v over dx. Okay, this particular expression and finally this expression equal to this. So you might wonder, how did we get to this form here, right? So this essentially, this particular form, what we got from this step on, we jumped here, and this form we got by solving this, by multiplying this matrix, by adding this matrix element and separating out into x, y and z components. And what we have here is just the x component of the equation, which is further simplified here, this whole equation, sorry. Okay, equation. Now, one of the things you might have also noticed is that when I was simplifying from this equation the different terms here, up here, the order of differentiation did not matter, and the assumption was made that order of differentiation does not matter. And what this means is that if the velocity components are smooth functions of x, y and z, then we can apply this irrelevancy of the order of the differentiation. That is something, the smooth function, I suggest you check it out, what the smooth function mean in your textbook. But smooth function as of x, y and z, if the velocity components are smooth function of x, y and z, the order of differentiation does not matter, and hence we get something of this form. Okay, now we further simplify this form such that we get from here on to this particular equation, and what we will get here is that you get, on further simplification, get rate of change of the velocity components with respect to x, y and z, which is essentially the continuity equation, which for an incompressible fluid, which is what we started of the assumptions, is del dot v is equal to 0, hence this term goes to 0, Then you have also del d square partial differentiation with respect to x, y, and z, and which is, this is the Laplacian, so essentially del squared u. So in its more simplified form, you have rho, this is the material derivative, minus rate of change of pressure with respect to x, this is a partial derivation, the velocity vector, plus mu del square u. This is the velocity u, x, and this is mu. Okay, so this is what we say as the Navier Stokes equation in x component. For all the vector components, we can write rho velocity components. But essentially, when you have a vector sign here, you know that depending on the coordinate system, you have to separate out into x, y, and z coordinates. The Navier Stokes equation, as I have said before, it's a cornerstone of fluid mechanics, and the rest of this particular textbook is devoted to just solving this. It is pretty much one of the classically unsolved equations, so we need to provide with assumptions and further approximations to come up with approximate solutions. So the rest of the text is devoted to solving this set of equations. And one of the things, why is it very difficult to solve? Why? Because it's second order, more specifically unsteady partial differential equation in 4 variables, and engineering math, what the class you have taken, we have probably never solved above second order in 2 variables. So it is kind of a very tricky thing to solve, at least in the scope of this class, and you have to apply softwares to solve it, which again I don't think we'll be doing it. So recapping, you have now 4 fundamental equations. One is the mass, which is the compressibility equations, del dot V. And the set of momentum balance. Next class we will see what type of problems could show up in the scope of this particular lecture and the scope of this particular chapter, on the use of these equations and what parameters to solve. I think it was made pretty clear on the continuity equation what type of problems can show up. Here too we have pressure as a component, as a parameter showing up. So what type of problems will show up we will see in the next class. Before we leave, those of you are interested, the continuity in the Navier Stokes equation in the cylindrical coordinate is of this form, and that's pretty much it for now.